uh, start of the quantum algorithms, right? And we checked the Dutch algorithm, okay, and which is constructed on the quantum parallelism, okay. So in today's session, we will go elaboratively, very slowly and elaboratively on the Dutch Joysa algorithm, okay. So in fact, if you just go through the Dutch Joysa algorithm, it is a generalized version of the Dutch algorithm, okay, right. So I would say Dutch Joysa algorithm is a very large one. Among that, Dutch algorithm is a part of it, okay. So that is what I meant here. Fine. Yeah. And it addresses a decision problem, okay, for a given function is a constant or balanced, will be found out by this Dutch Joyce algorithm across two partners or two points. Okay, one point is supposed to use a function which could be balanced or constant, and the other party would find out by seeking a less amount of queries for the first party. Okay, that is a Dutch algorithm. I'll explain using my blackboard notes, don't worry. And I'm just giving you an overview here. And this algorithm demonstrates an exponential speed up, very important, okay, which is possible through quantum computation, which is much more effective than classical approaches, where you need certain number of queries to find out whether the function is balanced or not, okay. And it is the one of the earliest example showing the power of quantum parallelism, okay, right. Okay, then now let's get back the problem statement. What is that? Okay, so let me use my hand notes, okay, right. So yeah, Dutch Joyce algorithm, okay. So what is this algorithm is all about? Okay, it is can be understood in a some kind of a game. As a game is much easier to understand. Let's say Alice is there as a one of the party, and Bob is there another party. Okay, both are sitting at different locations, right? Now, let's say Bob is using some kind of a function which is for any given argument x value, it is going to give a constant output. Okay, so let's say x value is running from 0 to 9, the 10 values. For all the 10 values, it is going to give a constant value for all x. Okay, right? The constant value could be 0 or 1. So if it gives 0 for the x for 6 fixed one x value, it keeps giving 0 for all the x values. Let's say for one of the x value it gives you 1. Then for all the x values, f of x values, it is gives you 1. So that is a constant mean. So there is another way this function can become. The function can become a balanced function. Balanced in the sense, for half of the input values, okay, for the half of them. So what I mean, let's say from 0 to 5 0 to 4 it gives you 1, half the input, half of the inputs, and gives you 0 for remaining another half of the inputs. For all the x inputs, if it gives you a constant function, it is termed as a constant function. If it for the half of the input it gives you 1, and for another half it gives you 0, it is a balanced function. So a given function can become two kinds. One is constant, another one is balanced. This is a function Bob is supposed to use. He is at different location. Now Alice has to find out what is this function, whether it's a balanced or a constant function. Now the Alice task is to figure out f of x is constant or balanced. She has to find out. Now she can't find out without interacting with Bob for sure. Now what she does, she picks a value, let's say x is equal to 0, and send to Bob. Bob feeds that to a function and he will get f of 0 and he sends back to Alice. Okay, let's say one query is one x value going out and f of x value coming in. Let's say that is a one query. Okay, right. Now if I look at this process, okay, right, if I look at it, the one query consisting of information of x argument value going to Alice and f of x value coming back to Alice from the Bob, and Bob is using f of x, a kind of a constant or a balanced. Now with the one value going in and f of x value coming to Alice, she cannot determine with a single query, she cannot determine whether the function is balanced or not, because the function may have a constant or a balanced kind of a structure. Okay, now let's say Alice again sends 1. Okay, if she sends 1, the x value goes to Bob. Bob calculates f of 1, sends back to Alice. Okay, on her lucky day, if x value going in, coming value is, let's say, earlier f of 0 value is coming out, value is 0. In the second query, let's say she gets 1. That is straight away she can say the function is balanced, because with just two cases 0 and 1 both are coming, which means it doesn't matter how many number of like queries needed, doesn't matter. With just two attempts she can find out the function is balanced. This is the best day, this is our best day, luckiest day I would say. She can find out. Let's say it is not her lucky day, okay, and what she got is, let's say, 0 instead of 1. Now what is the situation is, Alice has to do few more queries to find out, okay, few more queries to find out whether the function is balanced or not. Let's say she sends another value to Bob. Bob calculates f of 2, sends back to Alice. Probably if, let's say first time is, second time is not lucky, third time she gets back 1, she can now claim it's a balanced function. Okay, with the third time, let's say she did not get 1, if she gets 0, which means she has to do one more attempt. Now this can go on like this. Okay, now how long this has to go on? Let's say she has in her possession, okay, the x values, let's say x values running between 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say she has 9 values. Among the 9 values, she starts feeding the x values to Bob. Bob calculates f of x values and sends back to Alice. Now, how many maximum, the optimal maximum number of required attempts or queries for Alice to find out in this case is, okay, if the Bob function just only takes values from, let's say, Bob function can only take values from 0 to 9 only. Let's say that is the situation. It cannot take anything more than 9. It only takes 0 to 9. Okay. So in that case, what is the worst scenario which takes a maximum number of attempts for Alice to find out is very simple. There are 10 attempts, sorry, 10 argument values. Okay. So 10 argument values up to okay, sorry, up to n equal to x is equal to 4, she may get back f of x values being 0, 0, 0, 0, 0, right? So whether it's a constant or balanced, in both the case, up to 5 input argument cases, the function can have zeros. But if you notice, the next number, the sixth attempt here in this case, will going to decide the function is balanced or not. You know why? For the half of the values, it has to be 0 or 0, and for the remaining half, it has to be 1 in the case of balanced function. Okay? In the case of constant function, it has to be zeros for all the cases or ones for all the cases. Since it is 0 for the first 5, okay, for the sixth argument input, it has to take a value either 0 or 1. If it takes, let's say, if it takes a 0 value for the sixth argument input, so straight away there is no need to calculate the remaining numbers. Okay, you can say, or Alice can say, the function is constant with the output being 0. So how many number of attempts are required for her in this case? Okay, so 10 argument values divided by 2 plus 1. So which is 5 plus 1. 6 attempts are required on a worst day for her to determine the function is balanced or not. Let's say for the sixth attempt, let's say she got 1. Okay, she can simply conclude the function is balanced, and she may not need it to send any other further argument values to Bob to calculate. Okay, and so she will just conclude the function is balanced with the output 1. And how many attempts are again required for her? 10 plus 1, which is 5 plus 1. 6 attempts are required on our worst day to find out the function is balanced or not. Okay, now to generalize, okay, let's say Bob's function f of x could be constant or balanced with it is a capability to take arguments range, arguments ranging from, let's say, 0 to 2 to the power of n minus 1. Okay, so 2 to 0 to 2 to the power of n minus 1 numbers it can take, means it can take 2 to the power of n numbers. In that case, Alice has to send how many queries? Okay, how many queries she has to do to find out whether the function is balanced or not, simply the total number, what is the total number? 2 to the power of n divided by 2 plus one number of attempts, or I would say queries required for finding the function is finding the f of x is balanced or constant. You see, this is just an extension of previous case. In the previous case, what is 2 to the power of n? 2 to the power of n is 10. Okay, so 2 to the power of n by 2 is just 10 by 2, which is just 5. So 6 attempts are required in the previous case. Here in this case, 2 to the power of small n. Now, why did I represent the total number by 2 to the power of n is, if I have a data which is a capital N data size, if the data size is, our input argument numbers size is capital N, let's say capital N number of data points are there. If you want to feed those data points onto a computer, a quantum computer, what you would be doing? You will take small n number of qubits so that 2 to the power of n is equal to the capital N. Then only you can feed all the data points into the quantum qubits. Okay, at least you take 2 to the power of n must be greater than or equal to capital N, but never less than to n, because if it is less than to n, some of the data points you may lose, no, and you may not have a chance to feed it to the quantum computer. Okay, so the classical algorithm, I would not say classical algorithm, I would say the simple logic, right? So there is a possibility that Alice may not find for every possible scenario. She has to wait on her maximum number of attempts to find out whether the function is balanced or not. Okay, so 2 to the power of n by 2 plus one number of attempts are required to find the function is balanced or not. Okay, fine. So this is a game for us. Now the question is there any way we can reduce? The question is there any way we could or anyone can reduce, okay, right, 2 to the power of n by 2 plus 1 to a smaller number? Okay, that is a question one can ask. Of course, there is a possibility you can reduce this number to much smaller using a classical algorithms. Answer is using some classical algorithms. It is possible. Okay, but let me tell you another powerful answer. If we could, or Alice could, if we can use quantum computing and using quantum information embedding, quantum information processing, if we could do or we could incorporate, then 2 to the power of n by 2 plus 1 could be reduced to, you know how many? Just 1. With one query, we can find out, or at least can find out, the function is constant or balanced. Very important thing is we should use the quantum information processing. Okay, so how is that is possible is actually a Dutch-Joyce algorithm. Okay, so what is this Dutch-Joyce algorithm is? It demands few things. Okay, so DJ success demands a few things. What it demand those few things? Number one, all the query registers, sorry, all the queries must be, okay, converted into a quantum registers. Okay, that is done. Okay, all of them must be converted into quantum registers. And number two, those registers, the query registers, okay, plus one ancillary register, one ancillary register must be sent to Bob, okay, where Bob process it, okay, and he process it using, okay, he process it using his function f of x. You know how? It's a quantum information. Now he processes, instead of using f of x, he comes up with a unitary function, unitary gate function, okay, and sends back the f of x values in terms of quantum qubits back to Alice. Okay, all queries must be connected to quantum registers by Alice. Now, Alice receives in the last stage, Alice receives, and whatever is received, okay, she receives, analyzes, and figures out, okay, the f of x nature in one query. So she bundled all her functional value, all the x argument values, sent to Bob. Bob processes it and sent back to Alice. And Alice takes them and finds out whether the function is balanced or not. Okay, fine. So now how she will bundles all her query registers into one channel, and how she does add a ancilla qubit to store the information of all the functional values. Okay, so that you can understand using a simple quantum circuit, which is in fact an extension of a Dutch algorithm. Okay, so let me show you what is this DJ circuit, Dutch Joyce algorithm circuit. Okay, it consisting of, if you remember, a unitary oracle function u of f. It takes argument x value and ancillary register y, sends back argument x value as it is, but when it comes to ancilla, it flips this nature of f ancilla by adding with addition modulo using f of x. Okay, so now there is an input query register, there is ancilla, input query comes as it is. Okay, there is target register comes by having some change, right? This is a unitary oracle function, oracle function. Now the question is, this is in a way a kind of a Dutch algorithm. We need to do more. What is that more is, I have to feed the information of all the queries into one query register, which is done using a set of Hadamard gates. Okay, how many it needs? Whatever number of qubits I would be needing, that many I will be sending. How many are there? N are there. Okay. Now, when it comes to ancilla, I start the ancilla with the 1 and I even use one Hadamard here. Okay, one Hadamard. Now, at the query part, I will also use a same number of Hadamards. Okay, so I'll then get back. So this is a quantum circuit for Dutch-Joyce algorithm, which is in fact allows to find out whether the function is balanced or not. Okay, where the function information is carried, it is carried in terms of unitary function u of f. Now, what is the Alice role here? Alice role is at the left hand side. She prepares and adds ancilla qubit and query qubits and combine them, send to Bob. What is the role of Bob? Bob just process it using unitary function. Okay, he does is f of x value, feeds that f of x value into the ancilla qubit, so that is sent back to Alice. So what is sent back to Alice? Whatever is the output here, that output is sent back to Alice. Okay, and that output Alice figures out and analyzes it. Now, if you look at this circuit, it consisting of various stages. What is the number one stage? Number one stage is at the very starting. I'll call it as a quantum state psi 0. And what is the number two? Number two stage is quantum state psi 1. What it consisting of? It consisting of Hadamard's acting on psi naught. And after the unitary function, I can have one more quantum state, psi 2. Okay, after the final set of Hadamards, I will say there is another quantum state. I'm sorry. Now, if you see, there are 4 layers involved in this quantum system. Now, if you can understand step by step what happens in this quantum circuit, you would really appreciate what is the role of this circuit in the Dutch algorithm. Okay. Now, let's find out what is the psi naught. Psi naught is how many qubits are there? N qubits are there. All of them are in the zero state initially. And there is a 1 qubit ancilla qubit, it is in the excited state. Okay, now what is the psi 1? Psi 1 is a set of n Hadamards acting on the n qubits are in 0 and 1 Hadamard acting on 1 qubit. Okay, there may be a tensor product in between, but I am not writing. You can think that it is there by default. Okay, this is psi 1 for you. Now, what is the psi 1? Psi 1 is very simple. You can say, okay, let me write down here. There is a tensor and tensor n. You can say, you can put that outside. You can say the overall is tensor n and h acting on 1. So which is going to be a superposition of 0 plus 1 divided by square root of 2 and overall tensor n multiplied by 0 minus 1 divided by square root of 2. This is the psi 1 for you after the n plus 1 Hadamards acting on psi naught. Okay. Now, let's understand the psi 1 very, very carefully. Very important to understand psi 1. Okay, so for a generic n, you might not look and get some insights, but let's say for n equal to 1, n equal to 1 case, n equal to 1, what is the psi 1? Psi 1 would be 0 plus 1 divided by square root of 2 multiplied by 0 minus 1 divided by square root of 2. That's all. Very simple. But when it n equal to 2 case, what is the psi 2 would look like? Sorry, psi 1 would look like. Psi 1 would be 0 plus 1 divided by square root of 2 tensor square multiplied by 0 minus 1 divided by square root of 2. Okay, right? So now the left hand side, that is the first term is, it's a square. Okay, tensor square. What is a tensor square? Tensor square is just adding one more time, multiplying by one more time. Okay, what is this? It will be 0 0 plus 0 1 plus 1 0 plus 1 1 divided by square root of 2 into square root of 2. It's just 2. So what I will be getting here for psi 1 for n equal to 2, I'll be getting 0 0 plus 0 1 plus 1 0 plus 1 1 divided by 2 multiplied by 0 ket minus 1 ket divided by square root of 2. This is a psi 1 for you. Okay. Now in a shorthand notation you can write, because why did I am bringing shorthand notation here, because as n equal to 3, if I go, the the first query part would increase in size. It will go to 8 bits. 8 bits. Right now it's 4 bits. It becomes 8 bits for n equal to 3. If it goes to n equal to 4, it becomes a 16 bits. So I should have a shorthand notation to write my psi 1. What do I do is, I will say there is a summation over x. X belongs to 0 ket comma 1 ket square tensor square, where x ket divided by square root of 2 to the power of 2. What is 2 to the power of 2? It is just 2. Okay. Why instead of writing just 2, why I am writing square root of 2 to the power of 2 is, it will help me to write down a generic form for psi 1. What I mean is, for n equal to 2, this is the case. Okay, for n equal to 2. For any generic, for any n. Okay, for any n case, what is the psi 1 would look like? Psi 1 would be summation over x belongs to 0 ket comma 1 ket tensor n x ket divided by square root of 2 to the power of n. That's all. Okay. So for any case, any n case, for any n, okay, for n, any value, right? So for any n value, this is what I have. So as per my circuit, now I know what is the psi 1 would look like for any n value. Okay. The next question is, what happens after that? What happens after that? There is a unitary gate, unitary function, which takes the x query, which takes the input ancilla, it does the operation like this. Okay, so this is the, at this point I have a psi 1 which goes on becomes to psi 2. What is a psi 2, by the way? Psi 2 is unitary function acting on psi 1. Okay, this is the psi 2. Now how should I find the psi 2? Okay, how should I find that? By the way, I am missing something. You please correct me. What is I missing? Ancilla part. The ancilla part we missed to put it up. See, that is missed to put it up here. So which I am going to put it as 0 ket minus 1 ket divided by square root of 2. Okay, right? Let me remove this and then put it up. Very, very important. If you miss, then it will be very tough to recollect. 0 minus 1 divided by square root of 2. Okay, right? So, very good. The psi 1 we know, and now I have to find the psi 2. Psi 2 is what? Psi 2 is a unitary action on psi 1. By the way, yesterday we saw if there is a x comma y, okay, if a unitary function is acted on x comma y, what we will say? X remains the same, but y gets changed by addition modulo with the f of x. Okay, that we found, right? Now, if you just take for n equal to 1 itself, for n equal to 1 case, if you just see, okay, n equal to 1 case, let's say I have n equal to 1, I have x is equal to 0, y is equal to like that. If unitary function is added, so what I'll get? I'll get 0, y plus f of 0. This is what I'll get. Okay. Now, for n equal to 2 case, let's see. N equal to 2 case. Okay. Sorry. N equal to 1 itself, there is another possibility. What is another possibility? If x is equal to 1, I'll have 1 comma y plus f of 1. Okay, right? So this is there. Now what I will do, I'll just give you a simple scenario where, okay, where if some generic x is there, okay, my query register is, let's say, 0 comma minus 1 divided by square root of 2. And now consider unitary function acting on this overall thing. What is the unitary function? Okay, there is a query part, there is a ancilla part. It's a control, this is a target. Okay, so as per this, what we see here, okay, the effect is 0 plus, okay, right? Okay, let me write down explicitly. Unitary acting on x cat 0 cat minus x cat 1 cat divided by square root of 2. This is what I have. Now, what would be the output? X cat 0 plus f of x minus x cat 1 plus f of x divided by square root of 2. Now, if you see the output, x cat f of x cat minus x cat 1 plus f of x, it's a cat divided by square root of 2. Now, this is the output. Now, for f of x is equal to 0, what would be the output? Output would be x cat for any x. Okay, for any x. Output would be 0 cat minus x cat. 1 plus 0 is 1 cat divided by square root of 2, which is x cat 0 cat minus 1 cat divided by square root of 2. Okay, now for f of x taking one value for any x, in that case, if you just see what will be the output, output would be x cat 1 cat minus x cat 1 plus 1 is 0 divided by square root of 2, which is equal to, if you just take a minus common, I'll have x cat 0 cat minus 1 cat divided by square root of 2. So what it is conveying? It is conveying For either case, for f of x is equal to 0, I am getting a plus sign. For f of x is equal to 1, I am getting a minus sign. So I can simply say a generalization which is equal to minus 1 to the power of f of x, x cat, 0 cat minus 1 cat divided by square root of 2. This is called a phase kickback. Why it's called a phase kickback is, if you see the nature of minus sign in the nature of minus sign in the ancilla part is actually coming to the query part, control part. So usually the control will remain as it is, that is going through a C naught gate. But here in this case, the control amplitude is getting some negative phase depending on the functional form. Okay, so that means you can now conclude, okay, what is the conclusion is, unitary function acting on some x control, query is being a negative superposition, is equal to simply minus 1 to the power of f of x, x cat 0 minus 1 divided by square root of 2. Okay, this is the result which we will be using to find our psi 2. What is the psi 2? Psi 2 is unitary action on psi 1. By the way, what is the psi 1? Psi 1 is summation over all the x belongs to 0 cat comma 1 cat tensor n, x cat divided by square root of 2 to the power of n, 0 cat minus 1 cat divided by square root of 2. Okay. Now, as you know, unitary function doesn't depend on any n. You can straight away send it inside. Okay, what is that? Summation over x belongs to 0 cat comma 1 cat divided in tensor n, unitary acting on x cat. If you want, what you can do, you can send, okay, you can send 1 by 2 to the power of n to the start. Okay, so this is 0 cat minus 1 cat divided by square root of 2. Okay, now we just found out this result. We just substitute that result here, which is going to be psi 2 is going to be summation over x belongs to 0 cat comma 1 cat tensor n 1 to the power 1 by 2 to the power of n minus 1 to the power of f of x, x cat 0 cat minus 1 cat divided by square root of 2. That's all. I found what is the action of psi unitary function uf on psi 1 to give psi 2. Okay, see, I just found what is the psi 2 coming. Okay, right, it's so straightforward, it's very simple. Now if you want, you can find for n equal to 1, what is the how psi 2 would look like. Okay, if you want, I can show you. For n equal to 1, I'll have x belongs to 0 cat comma 1 cat minus 1 to the power of f of x 1 by square root of 2 x cat 0 cat minus 1 cat divided by square root of 2. So which is going to be, okay, what I'll get? I'll get minus 1 to the power of f of 0, 0 cat minus plus minus 1 to the power of f of 1, okay, right, as 1 cat divided by square root of 2, okay, 0 minus 1 divided by square root of 2. This is what I'll get. Okay, and for n equal to 2 also you can derive. How it would look like? It would look like minus 1 to the power of f of 0, 0, 0, 0 cat plus minus 1 to the power of f of 0, 1, 0, 1 cat plus minus 1 to the power of f of 1, 0, 1 0 ket plus minus 1 to, okay, minus 1 to the power of f of 1 1 1 1 ket divided by 2 to the power of 2 square root, which is simply 2 multiplied by 0 ket minus 1 ket divided by square root of 2. This is what you will find for n equal to 2. Okay, right? So for generic n, what we have is at the top, this equation. For n equal to 1 we have, for n equal to 2 we have. You can write for n equal to 3 also. It's easy. Now, what else I have to do? I have to do what is the action of a set of Hadamard's on the query part, okay, and nothing else. The identity on the ancilla part, so which is going to give me the psi 3. Okay, so what I mean is, after the unitary function, okay, after the unitary function, okay, I have n Hadamard's here and nothing on the ancilla part. So I'm just talking about this. At this point, I have psi 2. At this point, I'll get psi 3. So what is the psi 3? Psi 3 is a Hadamard, n Hadamards acting on query part and one identity acting on the ancilla part. Okay, that is I want to find out. Now, my target is to find what is my psi 3. So to go there, before going to psi 3, I will just introduce some shorthand notations. What kind of a shorthand notations I'll introduce is, okay, okay, right? So before going to find psi 3, okay, let's introduce some shorthand notations which are going to be very useful, okay, useful for later. Okay, so what are those things? I'll just bring it now. Okay, so what I mean is, you just take Hadamard, okay, consider Hadamard H action on some generic state X. Okay, right? So that where X is acting on, sorry, H is acting on X. Okay, now unless I don't know what is the X, I can't find out what is the result would look like. Okay, let's say now consider if X is equal to 0, right? If X is equal to 0 implies what? H acting on 0 would give you what? 0 plus 1 ket divided by square root of 2. Very simple. Now what I do, I want to write that in a shorthand notation. What is the shorthand notation? Already I am using X, so let's introduce some different variable. Let's say I'll introduce some small z. So which is small z, I'm sorry, small z, okay, small z ket divided by square root of 2. What I mean is, when z belongs to 0 comma 1, I will get both these situations. Now let's say consider if x is equal to 1. In that case, what happens? H acting on 1 give you what? It give you 0 minus 1 divided by square root of 2. Now if I had to write down a shorthand notation here, what I'll write? Summation over z belongs to 0 comma 1 minus 1 to the power of z, you see, z cat divided by square root of 2. This is what I'm doing. What I mean is, when z is equal to 0, I'll get the first entry. When z is equal to 1, I'll get the second entry. Okay. Now, is there any way I can generalize for all the above cases? Yes, it is possible. What is that is? H, carefully if you just see, H acting on X could be equal to summation over Z belongs to 0 comma 1. Okay. Now I'll just play a small trick. Minus 1 to the power of X into Z. Okay. Z cat divided by square root of 2. Okay. Square root of 2. This is what I am going to do. Now, if you see, when x is equal to 0, you take, I'll get the first. When x is equal to 1, I'll get the second. So, both the above cases are incorporated on Hadamard acting on some generic x. Now, the question is, this is for only x being either 0 or 1. Okay, that is a n equal to 1 single qubit case. Okay. Now, for n equal to 2, that is 2 qubits case. What is a 2 qubit? In case of 2 qubits, x can be having a values 0, 0, 0, 1, 1, 0, 1, 1. Now, in that case, how many Hadamards I will be acting to? Okay, so 1 Hadamard for 1 qubit. So, I'll have 2 Hadamards acting on x there. Okay, remember, now x is not a single entry argument, it is going to have 2 arguments. So literally my x cat is equivalent to some x1 and x2, where x1 can be 0 and 1, where x2 can be 0 and 1. So when I say x acting square, 2 Hadamards acting on x is equal to 1 Hadamard acting on x1, another Hadamard acting on x2. Okay, so that is what I mean. Now, let's generalize the above case. What is the above case says? H acting on some single argument is going to give me minus 1 to the power of x into z, z cat divided by square root of 2. So that means in this case, I will say summation over z1 belongs to 0 comma 1 minus 1 to the power of x1 z1. Z1 cat divided by square root of 2. This is one. Another one is Z belongs to 0, Z2 belongs to 0 comma 1 minus 1 to the power of x2 Z2. Okay. X2 Z2. Okay, multiplied by Z2 cat divided by square root of 2. So this is what I have, Hadamard square acting on x, where x being x1 and x2. Okay, for a 2 qubit system. Now what are we asking? We are asking for n qubit system. For a n qubit system means my for n qubit system. Okay, for n qubit system means h n tensor times acting on x. Remember, what is the x here? X here is x1, x2, how many? Xn. Okay, xn, right? So that is what I'm asking. Now what I will do, see, if you carefully look at this, there are two summations involved. So for n summations you will be involved. I simply say, okay, what I will be saying, x belongs to, sorry, z belongs to, okay, 0 comma 1 tensor n, okay, minus 1 to the power of x1 z1 plus x2 z2 and so on xn zn. Okay, so that will cover all the minus 1 to the power ofs, and in the ket notation I will say z1 z2 up to zn divided by square root of 2 to the power of n. Okay, where z belongs to 0 comma 1 tens to the power of n means z is actually z1 z2 and so on zn. Okay, so now I just know what is the Hadamard acting, n Hadamards acting on some quantum state where there are certain x, different x values are there. So even in the shorthand, much more shorthand notation, you can write down that h n tensors acting on this is equal to z belongs to 0 comma 1 tensor n minus 1 to the power of, now I'll write like a vector multiplication dot product. Let's say x vector multiplying to z vector with a dot product, I'll have z vector divided by 2 to the power of n. Okay, much more concised, okay, form, right? So this is what I am going to use, we will use to find psi 3. Okay, so let's get back where we're at before getting into this. Okay, a shorthand notation. Okay, where is that shorthand? Yeah, before going into this shorthand notation, where we are at finding what is the psi 3, where psi 3 is a set of photomods acting on psi 2. But what is psi 2 consisting of? Psi 2 is consisting of, see, some x is there. So Hadamard, some n Hadamards acting on the x would give me some output. What is that output would be? That output is a shorthand notation we just found right now. We'll use it and we will derive what is the psi 3. Okay. After deriving the psi 3, we will analyze the psi 3 and find out how Dutch-Joyce algorithm works. So what we'll do now, we'll take a quick 5 minutes break and we'll come back. It's 5:32. We'll come back at 5:37. Okay, everyone, welcome back. Right. So now we want to find what is the psi 3. Okay, right. So let me write down where we are at right now. We are at finding psi 3, which is n Hadamard's acting on, okay, query part, and identity acting on, okay, the ancilla part. By the way, what is the psi 2? Psi 2 is, okay, so let me recollect. Psi 2, okay, psi 2 is this. Yeah. Psi 2 is summation over x with 1 by square root of 2 to the power of n minus 1 to the power of f of x multiplied by x cat 0 minus 1 divided by square root of 2. That is the psi 2. Psi 2 is summation over x belongs to 0 comma 1 tensor n minus 1 to the power of f of x 1 divided by square root of 2 to the power of n x cat 0 minus 1 cat divided by square root of 2. This is the side. Okay. Have I missed anything? Let's check. Let's check. Have I missed anything? No, nothing we had missed. Okay. So let's now, we just found out, found out H tensor n acting on the x is equal to summation over z belongs to 0 comma 1 tensor n, okay, 1 to the power of 2 to the power of n minus 1 to the power of z into x. Bitwise, it's like a dot product. X, z into x, z cat, okay, this is we just found. Okay, now what I will do, I will use this result, okay, in finding my psi 3. Psi 3 is what? Psi 3 is summation over, okay, h acting on, n tensors acting on x belongs to 0 comma 1 tensor n minus 1 to the power of f of x 1 by 2 to the power of n square root x. Okay, this is Hadamard acting on this part, tensor, identity acting on the ancilla part. As we know, identity would not do anything. So only worrying I should do how Hadamard is going to affect the x. So let me put it inside. Summation over x belongs to 0 comma 1 tensor n minus 1 to the power of f of x divided by 2 to the power of n square root and Hadamard n's acting on the x. And remaining thing I'll just keep as it is. Okay. Right now we have this term. Let me put this term here. Now we have a very lengthy expression. So let me write that little bit smaller. So this is equal to summation over x belongs to 0 comma 1 tensor n minus 1 to the power of f of x divided by 2 to the power of n. Okay, now I'll bring the another summation from the above equation. Z belongs to 0 comma 1 tensor n 1 by 2 to the power of n square root minus 1 to the power of z into x. Okay, I'll not write the square arrow or above. You can think that it's a bitwise multiplication. Bitwise multiplication means z1 multiplied by x1, z2 multiplied by x2. Okay, so here I have z ket. Okay, right? So what else I should not miss out? Everything is taken care. Let me put 0 ket minus 1 ket divided by square root of 2. Okay, now there is a z summation, there is a x summation. What I will do, I'll put all the summation to the one end. Okay, so I can take it out, it's not going to affect. So let's put this summation all the way outside. Summation over z belongs to 0 comma 1 tensor n. Summation over x belongs to 0 comma 1 tensor n minus 1 to the power of f of x plus z dot x divided by, there is a square root of 2n, there is a square root of 2n, so which will become just 2n minus z ket 0 minus 1 ket divided by square root of 2. Okay, this is what psi 2 would look like. Okay, right? So psi 2 is, sorry, psi 3 is summation over z belongs to 0 comma 1 tensor n. Summation over x belongs to 0 comma 1 tensor n minus 1 to the power of f of x plus z dot x divided by 2n z ket 1 ket minus 0 ket minus 1 ket. This is the side 3. So this is what Alice gets back from the Bob. Now, this is the entire expression carries the information of all the qubits. She sent 2 to the power of n qubits to Alice, Bob. Bob processed it, and along with his query register, this is a, sorry, ancillary register, he sent back to Bob, Alice. Okay. Now Alice has to analyze this. Okay. Let's analyze carefully. Analyze psi 3. Okay. Now, yeah, right. So what I do now here, if you carefully look at this quantity, okay, x belongs to 0 comma 1 tensor n, z belongs to 0 comma 1 tensor n. Now let's take for the case, let's say for the n equal to 1 case, n equal to 1. Okay, what is the summation? Summation would be in z belongs to 0 comma 1. Similarly, x belongs to 0 comma 1. Obvious. Okay. Now for n equal to 2. Okay, in that case, if you notice, for n equal to 2, z belongs to 0 0 0 1 1 0 1 1, and x belongs to 0 0 0 1 1 0 1 1. Now there is an interesting thing happens for considering, for consider z is equal to 0 0 ket. Just to take that z equal to 0 0 ket, z ket is equal to 0 0 ket. Okay, for n equal to 2, I am trying to analyze what is my psi 3 would look like. Okay, right? So if you carefully see what is a psi 3, psi 3 is summation over, okay, if you want I can write down, for n equal to 2, psi 3 is summation over z belongs to 0 0 0 1 1 0 1 1, summation over x belongs to 0 0 0 1 1 0 1 1, okay, minus 1 to the power of f of x plus x dot z divided by square root of 2 to the power of 2, okay, z ket 0 ket minus 1 ket divided by square root of 2. This is what psi 3 for n equal to 2. Okay. Now The Z can be any four possible scenarios. What are the possible scenarios? Okay, Z can be 0 0 cat, 0 1 cat, 1 0 cat, or 1 1 cat. Okay, if Z falls to 0 0 cat, what I mean is when Ali's measures are psi 3, it has a query part, it has a ancilla part. So when she measures only, like, let's say she measures only query part. Okay, she just see what is the query which I got back. If it falls to 0 0, or if it exists in 0 0, means what? What is a 0 0? What is a 0 0 means? Which implies Z1 is 0, Z2 is 0. Why? My Zk is in fact Z1, Z2. Okay, in that case, if you notice, what is the corresponding amplitude? What is the corresponding amplitude? Probability amplitude. What is that? Corresponding amplitude is minus 1 to the power of f of x divided by square root of 2 square. Okay, but x plus x dot z is not there because z1 is 0, z2 is 0, which implies x dot z is simply 0. So I just simply say 0. This is the probability amplitude. Probability amplitude. Okay. Now, if you notice this probability amplitude, which is simply minus 1 to the power of f of x divided by 2. Okay. Now, the value of whether we get 0 0 as an output in the query is dictated by this probability amplitude. If this probability amplitude is 1, I'll get 0 0. If this probability amplitude is, let's say if this probability amplitude is 0, I'll not get 0 0 cat. Now let's say, okay, if f of x is a constant function. If f of x is a constant function means what? F of all values of x, it should give me 0 or 1. All zeros. Okay. All zeros. Okay. It's a constant function for me, which means minus 1 to the power of 0 divided by 2 plus minus 1 to the power of 0 by 2 minus 1 to the power of 0 by 2 minus 1 to the power of 0 by 2. What is the sum? Sum is 1 by 2, 1 by 2, 1 by 2. Okay. So it will be, I'm sorry, I have missed something. Okay. So what did I miss? Okay, it's a probability amplitude. So I have to square for the probability. So I have to square it. Okay. Right. So I'm sorry. It's not squaring. Yeah. So it's a probability amplitude is not a square root. I missed it. See, no square root is there. We should not miss that. So let me remove that. Square root is not there. Okay, square root is not there. It will be 1 by 4, 1 by 4, 1 by 4. Okay, I'm sorry with that. 1 by 4, 1 by 4, 1 by 4. Now, all of them are positives because minus 1 to the power of 0 is 1. So I'll get 4 by 4, which is equal to 1. So when the function is constant with all zeros, I'm getting 1. The amplitude or probability. Okay. Now, if the values are all 1, all ones. Your functional values are all one. In that case, what I get? In that case, I'll get minus 1 to the power of 1 divided by 4 minus 1 to the power of 1 divided by 4 plus minus 1 to the power of divided by 4 minus 1 to the power of. So the value here is just minus 4 by 4, which is minus 1. The probability amplitude is minus 1. The probability is obviously going to be 1. Okay, so doesn't matter whether the function gets all zeros or all ones. I am getting, okay, for a constant function I am getting a probability amplitude is equal to 1, probability is equal to 1. So let me conclude, for a constant function, for a constant function, okay, the probability amplitude or probability, I will not say probability amplitude, I'll just square it. Probability of getting z equal to 0, 0 is 1. Okay, right? Let's say a balanced function. Let's say a function is balanced. If f of x is balanced, in that case, let's understand. Okay, in the balanced case, let's say f of 0, 0, f of 0, 1, f of 1, 0, f of 1, 1 is there. So for the first half, I'll get 0. Second half, I'll get 1. In this case, what is the probability amplitude? Probability amplitude is minus 1 to the power of 0 by 2, sorry, by 4, minus 1 to the power of 0 by 4, plus minus 1 to the power of 1 by 4, minus 1 to the power of 1 by 4. What is this sum? It is a 2 by 4 minus 2 by 4, which is 0. So the probability amplitude is 0. Doesn't matter. First two of them giving 1 or second two of them is giving 1. For a balanced situation, a probability amplitude is 0. So looking at the 4 cases, if you see, first two cases where function is constant, and looking at the second two cases where function is balanced, you can just draw very broad conclusion. What is the conclusion? If the function is balanced, if the function is balanced, we would not at all see z being 0, 0. That means we will see something else other than this. Other than these. What are these? What are those? It can be 0, 1, it can be 1, 0, it can be 1, 1. So the final conclusion would be, if we measure query part of psi3, in case we get z is 0, 0, straight away you imply f of x is constant. If it is not, if that is not other than 0, 0, you can say function is balanced. Okay, so the what Alice can conclude is, now Alice measures the query part of psi3. She measures the query part of psi3, right? And in case if she gets, okay, if she gets, okay, if she gets z being all zeros, okay, n zeros, then she concludes, or she can conclude, she concludes that f of x is a constant. How did I do? I just generalized from n equal to 2 case. For n equal to 3 also you can just check. For n equal to 2 case, we just derived. And for n equal to 3, we can also prove. For n equal to 4, we can prove. And finally, we can say Alice simply measures her side 2, side 3 and see if it is anything other than zeros. If she is getting as a query part, she just say simply it is a balanced. If she gets all zeros in her query part, all of them in the ground state, all her query registers, means she can simply say it is a constant function. So in this way, okay, in this way, right? Okay, let me draw the circuit again for you people. Okay, so there is a unitary oracle function u of f. There is a x, there is a y, there is a x, there is a y plus f of x. Okay, Hadamard acting here, n Hadamards, nothing here, n Hadamards. Okay, and 0 tensor n's and 1 Hadamard here. There is a 1 ket here. Okay, so psi naught, psi 1, psi 2, psi 3. Okay, this is the DJ circuit. Alice prepares everything, sends to Bob. Bob processes it, and he sends. Okay, and even you can say this is what Bob sends back to Alice. What Alice does, Alice acts Hadamards, n Hadamards on the query. Okay, n Hadamards on the query, and at this point she makes a measurement, and that measurement is carried on a classical channels, and those classical channel information Alice analyzes from there. Okay, classical channels. Okay, and this is Alice. Okay, Alice Alice analysis by H action on queries. Okay, followed by measurement, followed by measurements. Okay, fine. So with one query, so all the x value arguments sent to Bob. Bob process it in one go and sent all of them to Alice. Alice will do the Hadamard action and then analyze, and from there she figures out what is the function. Is a balanced function or a constant function. In one attempt, Alice will find out. Okay, right? So this is a Dutch-Joyce algorithm for you. If you want, you can analyze for n equal to 3, n equal to 4, and so on, and just generalize. Okay. Now, I can just summarize. Okay, a summary of Dutch-Joyce algorithm. Summary of DJ algorithm. Okay. So I'll summarize in steps. Okay. Number one is, okay, number one is Alice will initialize. Alice prepares. Okay, she prepares n qubits are all in 0 and one query ancilla qubit in 1. She prepares. Okay, and then she acts. This is a psi naught, and then she operates n Hadamards on the query part and 1 Hadamard on the ancilla part on psi naught to get psi 1. Okay, what is it would look like? It look like 1 by square root of 2n summation over x belongs to, okay, right, 0 comma 1 tensor n x cat 0 minus 1 divided by square root of 2. Maybe we better put a square of 2 to the power of n inside instead of having outside. It's better to do that. Okay. Now that Bob takes, okay, Bob operates unitary function on the side 1 to get side 2. What is the side 2 would look like? Side 2 would look like x belongs to 0 comma 1 tensor n minus 1 to the power of f of x divided by 2 to the power of n square root x cat 0 minus 1 cat divided by square root of 2. Okay, Bob operates. Now Bob operates and whatever side 2 he get, he sends back. Okay, let's say Bob operates and sends back to Alice. Now Alice operates H n Hadamarts only on query part. Okay, to get side 3. So what is the side 3 would look like? Side 3 would look like, carefully now you see, summation over z belongs to 0 comma 1 tensor n, summation over x belongs to 0 comma 1 tensor n, okay, minus 1 to the power of f of x plus x dot z divided by 2 to the power of n z cat multiplied by 0 comma minus 1 divided by square root of 2. This is the side to Alice gets after Hadamard action. Next, Alice measures only query part of side 3. Okay, she concludes that function is constant when she sees z is all zeros. Okay, she concludes f of x is balanced when she doesn't see z is 0, 0, 0. If she's fine, straight away constant. If she doesn't see, then it is a balanced. That is a DJ algorithm for you. Okay, right? Fine. So with this, we just concluded Dutch choice algorithm. Okay. So if at all, if I have to recollect what have been done from the yesterday session, okay, remember we started with quantum parallelism, okay, which allows one to process multiple informations in one go. What is that? It allows you to find the function values, multiple function values in one go determination. You can determine multiple values. That is a quantum function for quantum parallelism for you. You add that quantum parallelism, okay, with if you add that to, okay, so quantum interference. You add that quantum interference. What you will get? You will get Dutch algorithm. What is the Dutch algorithm? Dutch algorithm is you not only find function values, you will also find the sum of the function values. You would able to find Okay, f of x1 plus f of x2 plus f of xn, and so on up to, sorry, f of x3, so on up to xn with the Dutch algorithm. Now, if you see now, earlier I said Dutch algorithm is a specific or a generic case of a Dutch choice algorithm. Now, if you implement that here, let's say if the function is balanced, sorry, function is constant, means all of them are zeros. Okay, all of them are zeros. What do I get? The sum is just simply zero. Okay, if all of them are ones, okay, if there are even sums, then also I'll get zero. Okay, obviously I'll be taking a even function. You know why? The our total number of qubits is 2 to the power of n, so the even function, so we are taking even numbers. Okay, even numbers we are taking. If the function is balanced, okay, in that case, okay, if the function is balanced, in that case we'll get 1. If the function is constant, in that case we'll get zeros. So that is a Dutch algorithm being a specific case for Dutch choice algorithm. Okay, now the first one is quantum parallelism, second one is parallelism plus quantum interference. Being Dutch choice algorithm is, okay, finding f of x being constant or balanced with minimal attempts, minimal queries. How many? That is simply one. Okay, so very, very commendable thing. Okay, so with this, we had ended the preliminary quantum algorithms, Dutch and Dutch JOISA. So in tomorrow's session, or let's say if somebody takes tomorrow's session, when I come back for another session, I'll be talking about Bernstein's Vajrani algorithm. Okay, next one is, it is slightly of same kind, and after that I will be discussing Simon's algorithm. Okay, more or both of them in a way the extension of whatever we discussed so far. Fine. So it's now 6:15. If somebody has any doubts, please let me know. Otherwise, we can just wind up at 6:15 itself. Okay. So what I will be doing, I'll be sharing this entire running note. Okay. And also my notes. Fine. Also my notes. And also I will share the PPT with you. Okay. So let me show you what is the PPT I want you to see. So it's like a text version of the summary, what I was doing today. So it's like a hints how exponential speed up is possible. Okay, so here see the function is constant, here the function is balanced. Okay, we need to find, okay, and in a classical fashion on a worst day we would be needing half plus 1 extra attempts. Okay, if I do a quantum oracle, use a quantum oracle, in a single attempt we can find. So what is the circuit? This is a circuit. Okay, and step by step, if you start finding what is a psi 1, okay, this is a shorthand notation for psi 1. And then what is a psi 2? Psi 2 is just minus 1 to the power of f of x come inside the psi 1, that is just the psi 2. So you get the psi 2, and then the psi 2 is a Bob's result. Bob sends to Alice. Now Alice applies a Hadamard n Hadamards on psi 2 and gets a psi 1. Okay, and if you are not getting, this is a summation under z. Okay, and there is a summation under x is there inside, and then psi 3, and Alice analyzes only query part and its amplitude. If she notices this, if the amplitude taking 0 value means z is not getting, z is equal to 0 0 0, she not appears. Okay, if it appears z equal to 0 0 0 0 appears, so she can simply say the f of x is a constant. Okay, a summary is again shown here. Okay, a key result here is there is only one oracle call required, and it always succeeds, and it demonstrates exponential speed up. Okay, right? Thank you. I hope it doesn't bore you. I went very, very slowly. So, what I tell you, people, so please go through either my notes or my running notes, okay, or PPT, whichever one you find it useful for you, and understand the Dutch choice algorithm. Okay, right? Fine. If there are no notes, I will just stop at this point. So, no doubts. Strange injustice. Any queries? Okay, there is a question here. Is psi 0 cat, cat 0 or cat 0 space cat 0 or okay, so let me understand what is the question here. Okay, Dr. Kupuswamy sir is asking psi 0 comma cat 0 plus cat 1 or cat 0 space cat 1. Maybe I think what you are asking I'm not getting, but I will request you to please just see at a very early stage I have a psi naught, which is tensor n on ket 0 and ket 1. That is a psi 0, which goes through n plus 1 Hadamard's and becomes psi 1. Okay, so that if you can understand, it will become easy. Now, for your own sake, I can derive a simple scenario. What is that scenario is n equal to 1. N equal to 1, there is a test zest 1 query. and another one is 1. There is one Hadamard going through, another Hadamard going through. This is my psi 0. Psi 0 is Hadamard acting on 0 and Hadamard acting on 1, which is going to give me 0 plus 1 divided by square root of 2, 0 minus 1 divided by square root of 2. This is n equal to 2. For n equal to 1, this is n equal to 2, tensor square, Hadamard square, okay, and just one Hadamard, this. So here psi naught would be Hadamard acting on 0, Hadamard acting on 0, and Hadamard acting on 1. So what is this? This is 0 plus 1 divided by square root of 2, 0 plus 1 divided by square root of 2, 0 minus 1 divided by square root of 2. So what is this quantity will give you? 0, 0 plus 0, 1 plus 1, 1, sorry, 1, 0 plus 1, 1 divided by 2. Okay, let me clear this. Okay, fine. So you can derive for the even other cases also. Fine. Yeah. It is a control bit and target bit you are asking. Okay, so that would happen in the unitary function. In the unitary function, it is something like this is a control, this is a target. Okay, so it's not a unitary function, you can say a unitary control function. Okay, right? So I am not specifying what is this oracle would look like. I would simply say the effect of oracle on the control, so on the target with the x being controlled. So what is here? I have x is my control and my target is 0 minus 1 divided by square root of 2, which is going to give me minus 1 to the power of f of x, x cat, 0 minus 1 divided by square root of 2. I hope now you will get it. Now I'll get your question. So this is a control, this is a target. Interestingly, control and target both remains the same, but there is a positive earlier probability amplitude of control is 1. Now it has become minus 1 to the power of f of x. So that is the phase kickback. This is the phase kickback. Phase is going to be acquired due to that control target being something else. Okay, I hope now you are asking that. So the control part is x, the top part, this is the control part, this is the target part. Okay, right, fine. So thanks for asking, Dr. Kupaswamy sir. Okay, yeah, let me save this again, PDF file. Yeah, done. DJ underscore algorithm notes. Save. Yeah, Satyan sir,
Thank
you can take over. Yeah.
Thank you so much, sir, for this informative session. Thanks to all the participants. We will meet at 3 p.m. tomorrow as usual. Thank you so much, sir.
Thank you, sir. Thank you. Thank you. Yeah. Participants, I'm uploading all the notes. Please check in the canvas.